All right, well, good evening, everyone, and welcome to a very stormy March Meet the Astronomer night with Vanderbilt Dyer Observatory. So I'm Dr. Billy Teets, and I'm going to be your host and your presenter this evening. So thank you all so much for joining us. Before we get started, I want to give a big shout out to my colleagues, Brian Smokler with VU News and Communications, who is making sure our stream is going out, and also Helen Morissette, who is my colleague at Dyer, who is going to be helping us with questions at the end. And speaking of questions, if anybody has questions throughout the program, please make sure to put those into the YouTube chat. We're going to hold the questions until the end, but if something pops in your mind, go ahead and pop it in the chat because Helen's going to be helping keep track of all these questions, and we'll try to address as many of those as we can at the end. And as I mentioned earlier, since it is a stormy night, hopefully I will not lose power, but if I do, I will contact either Brian or Helen and they'll let you know, and we'll just kind of go from there. But hopefully, fingers crossed, everything will go smoothly tonight. So before we begin, I have just a couple of announcements. We have some April events coming up. Again, these are going to be virtual as well. We have a talk on April 8th. It will be our April Meet the Astronomer night. Excuse me. And the talk will be by one of our newly minted PhDs, Dr. Laura Vega. So she's going to be talking about one of the star systems that she used in her PhD thesis, and talking about how there's been over 100 years of data from observations of this star. So we'll be talking about how that's taught us about this system, what we've learned about, and what questions there still are. And then on Saturday, April 17th, starting at 8 p.m. Central Time, we will have our April virtual star party. Hopefully it'll be clear so that we can do some stargazing and look at some objects that we have in the sky above us. Well, I'm undoubtedly be talking about some other topics along the way, so we encourage you to join us for that as well. That typically goes for about 2 hours, but details for all of these events can be found on Dyer Observatory's website, dyer.vanderbilt.edu. They're all virtual and they're all free, so we hope to have you all joining us there as well. So tonight we are going to be focusing on the Voyager missions. So I gave this talk, or a similar talk, I should say, last year for the Frisk Center. There was an exhibit that was put in that dealt with one of the aspects of the Voyager missions, which was the golden records that are found on both of the Voyager probes. And so the talk that I gave then was a little bit of background on the missions, but dealt more with the actual golden records. For this talk, we're going to be talking more about the probes themselves. So I'm going to start by giving a little bit of background about the kinds of instruments that they have, when they were launched, what the ultimate mission goals were. And then we're going to be talking about some of the results that came from these missions, some of the discoveries, some of the very notable discoveries. And then we'll end by talking a little bit about where these probes are now, what they're doing. And if we get time, I'll give you just a little tidbit about those golden records, okay? All righty, so the Voyager program, this was a program that started back in the 1970s. It was actually originally intended to be a larger program that dealt with exploring not only Jupiter, Saturn, Uranus, and Neptune, but also going to Pluto. But in the end, the program was scaled back a little bit, and we ended up with 2 probes, the Voyager 1 and the Voyager 2 missions. And so the Voyager program was really to embark on a grand tour of the solar system. So what do we mean by grand tour? Well, we sent probes to Mars, we started exploring the inner part of the solar system, but we hadn't explored the outer solar system all that much. Prior to the Voyager missions, we had Pioneers 10 and 11 that actually did visit Jupiter and Saturn for the first time and gave us our up-close views, our first up-close views, that is. And these programs, or these probes, as their name suggests, they were really pioneers for the exploration of the Jovian and the Saturnian systems. We knew, for example, that Jupiter was a very bright source of radio emission. And it was hypothesized that there was going to be a very intense radiation around the planet as a result of particles interacting with its very strong magnetic field. And so the Pioneer missions kind of went through there to kind of give us an idea of what to expect so that future missions would be built well enough so that they could easily withstand the environments and be able to transmit images and all sorts of data. This program would make use of an alignment of the planets that only occurs about every 175 years. So when we say alignments, we don't really mean what you're seeing on the screen. This is a nice kind of promo card for the Voyager program that was put together by Don Davis. But when we're talking about alignment, we're meaning that the planets are in the right positions in their orbits, and they're roughly in the same part of the solar system. Basically, all on one side of the sun, not too terribly far apart from one another. So we don't mean that they were all in a straight line with one another. That actually won't happen. But because of that alignment, that allows us to make use of a concept of a gravity assist or a slingshot effect. By traveling to one of these planets, we can use the motion of the planet, its gravity, and the concept of momentum conservation to get our probe accelerated faster and go on to the next planet. And then once we get to that next planet, we can use that planet as a slingshot to get us to the next destination, and so on. So if we have the planets kind of spread out, then we're not going to be able to do that slingshot where we go from one to the next, to the next, to the next. So the engineers and scientists who were working on the Voyager program had a very limited time frame to get everything completed and launched. Otherwise, we would miss that window and we might only be able to go to one or two of these planets. So I also want to mention that, on a personal note, these missions are very important for me because they were launched in the late 70s. I was a child growing up in the 80s. So the books that my friends and family gave me as I was growing up had a lot of the images from these missions. And being a child and really having the whole concept of astronomy really starting to take hold and really gaining an interest in it, seeing these images, they're really ingrained in on me. So, for example, when we look at new images of Jupiter from the Juno mission, those images are much higher resolution than what the Voyager missions had, and they are truly spectacular. However, seeing some of the images that I saw as a kid have more of an effect on me. They really evoke a feeling. So these missions are kind of, for me, kind of personally important just because they kind of influence my path through life and how I got to where I am today. So anyway, let's talk a little bit about the probes themselves. So here is a model of one of the Voyager probes. So Voyagers 1 and 2 were identical spacecraft. They had similar targets, but their missions were not the same, as we'll see in just a moment. I just want to point out a few of the different characteristics of these probes. So one of the hallmarks is this large dish that sits on top, and you often see it pointing up like this. This was the high gain antenna. This is the part of the communication system that allows signals to be received from Earth and be transmitted back to Earth, especially when the spacecraft is well far away from the Earth. So we'll talk about how that occurs a little bit later on. Off to the side are some of the instruments. Obviously, there are lots of images that came back from the Voyager missions. The cameras are located in this section here. We've got spectrometers as well, which don't really image so much, but they give us more information about things like temperature and composition and so forth. You may be wondering what this little plate is down off to the side. That's actually a calibration source for the optical or the instruments that can see in the type of light we see, and also for the infrared instruments. So it's kind of like a way for the cameras or the instruments to turn and adjust their kind of like their exposures and whatnot, so that it's kind of like the cameras are doing a white balance. So that was their source to say, okay, here is our, you know, our white, if you will. So it allows for a more accurate representation of the final images. We have cosmic ray and particle detectors. So these cosmic rays are essentially just free charges. They could be electrons, they could be protons, but these are free charges that are traveling through space. If they have low energy, that means that they're going slower. So our sun would be a good source of cosmic rays, or in other words, low energy cosmic rays. But outside of our solar system, as we'll be talking about at the end, we can detect very high energy cosmic rays, which would be things that are, or cosmic rays that are coming from events like supernovae, where particles can be accelerated to incredibly high velocities. We've got other instruments like the plasma wave detectors. So these will monitor for radio emissions around the planets or in the local environment. The antennas that we're seeing here are actually much longer than what is pictured in this view. Now, what is not shown on here is another one of the hallmarks of these missions, and that's the magnetometer boom. You may have noticed it in the very first slide. In fact, let me go back to that one. So this piece right here, and it looks not too terribly long, but it's just a viewing perspective. And so the probe is kind of turned at an angle. This boom is actually, it would go well off the slide here. It'd be about 40 feet long. For size comparison, this dish is about 12 feet wide. So from the ground up to the top here, that's about 12 feet. Okay, so these probes were not small, but the magnetometers, especially the very sensitive magnetometers, had to be placed at a good distance away from the spacecraft so that the instruments on the craft itself did not create a magnetic field that the magnetometers would detect. We only wanted to detect the magnetometers coming from space and from the objects of study. One thing you will not see on the Voyager missions are solar panels. Typically, when we're talking about spacecraft, even like going to Jupiter with the Juno spacecraft, we often see solar panels. But the Voyager missions did not have solar panels because once they started getting far away from the sun, like if they're out around Uranus or Neptune, the sun's going to be much dimmer, and the solar panels are not going to be able to provide enough power to be able to power these craft. So instead, these are nuclear powered. So RTG stands for radioisotope thermoelectric generator. Inside of the three modules here are spheres of pressed plutonium-238. That is a radioactive material that will decay, or the technical term is fission, into other elements. That process releases energy and in the form of heat. So that heat can then be collected by devices called thermocouples and actually converted into an electric current. So as the material in here decays and heats up, we're taking that heat, converting it to electricity. The half-life of the plutonium-238 is about 87 years, which means that if we started out with a full complement of plutonium-238, about 87 years, we would see that half of that had decayed completely, okay? And as that decays and we have less plutonium, then we're going to have less and less power being produced. So that's going to limit the lifetime of these missions, as we'll talk about in a little bit. And then finally, hopefully we'll get a moment to talk about at the end, are the golden records, another one of the hallmarks of the Voyager missions. So these are actual records. Think back to the technology of the time. This is 1970s, so we're not dealing with DVDs and MP3s and things like that. We're talking about the old style phonograph records, but these were coated in gold, and they actually contained sounds and images encoded onto the records. And so they were kind of like a message in a bottle in case some civilization in the future came across this craft going through space. So when were these guys launched? So first of all, they were launched from Cape Canaveral, Florida, aboard the Titan IIIe Centaur rocket. You may think Voyager 1, given its name, would be launched before Voyager 2, but in fact, it was launched about 2 weeks after Voyager 2. Um, the Voyager 1 would end up getting to Jupiter first because of the trajectory that it was put on. Voyager 2, when it was launched, it was put into a little bit more circular trajectory. So one of the reasons for that is that it had a slightly different mission or potential mission goal than what Voyager 1 would have had. And so their trajectories were a little bit different at the start. So what were some of these mission goals? So Voyager 1, even though it was launched before, or excuse me, it was launched after Voyager 2, ended up getting to Jupiter first because of the path that it was sent on. So its mission had 3 main goals. The first was to do a flyby of Jupiter. And so keep in mind, when we say flyby, it's a literal flyby. We're not going to Jupiter and going in orbit around it and making multiple observations. We're actually taking images as we're coming up to it and taking images as we're passing by it and leaving it. So there's no stopping and orbiting. We're just kind of going on past it to the next target. So as it was doing the flyby, it would be taking images of the planets, and moons, and trying to gain as much data as it could. Using Jupiter's gravity and Jupiter's motion around the sun would allow us to accelerate Voyager 1 then onto Saturn. And when it encountered Saturn, it would study the planet, its rings, its moons. But there was a third target of interest that was also with Saturn, and that was its largest moon, Titan. So we had known for a while that Titan had an atmosphere. The Pioneer missions did get close-up images of Titan, which piqued astronomers' interest even more because the results that came back suggested that it had a little bit more to it than what met the eye. So it was a prime target of study. It should be noted that if Voyager 1 had gone to Saturn, its trajectory could have been altered so that after doing a flyby of Saturn and not doing a flyby of Titan, it could have actually gone on to Pluto. So the mission specialists had a choice. Do we go to Titan or do we go to Pluto? Well, Titan was more scientifically valuable, or it was viewed in a more scientifically valuable light, so it was decided that we would go to Titan. So it is the only moon in the solar system with any appreciable atmosphere. So let's talk about some of the results of the Voyager 1 mission. So it was launched, and a couple of years later was already at Jupiter. So in early 1979, we encountered Jupiter. I mentioned before how some of these images really evoke a feeling for me. This is one of those because being a young child, this was on the cover of one of the books that I constantly flipped through. So, this image is near and dear to my heart. This is a nice Jupiter or Jovian family portrait, as we would say. It's actually multiple images put together. So we see Jupiter in the back here with the great red spot, big storm on Jupiter that's been going for hundreds of years. You can see features and the clouds themselves. And then you see the 4 largest moons of Jupiter. Those are known as the Galilean moons, named after Galileo, who discovered them with his very small telescope in the year 1610. If you have a telescope, doesn't matter what size, if you see Jupiter in the night sky, you can look at it each evening and see these moons. But they're shown in order that they are from Jupiter. So closest in is Io, which we'll come back to in a moment. Then Europa, Ganymede, the largest moon in the solar system, actually bigger than the planet Mercury, and then Callisto over off to the side here. So 3 of these moons, all of them except for Europa, are a little bit larger than our own moon. They're not like 2 or 3 times larger, but they're on the order of some of them a few tens of % larger. So our moon is actually number 6 if you rank the moons by size in the solar system. Europa is a little bit smaller. But again, it's a nice family portrait. So here is a nice animation showing some of the images that were taken as Voyager 1 was approaching Jupiter. you'll notice that the planet looks like it's basically sitting still, but you can see the motion in the clouds. We knew the rotation rate of Jupiter pretty well. It's 9 hours, 56 minutes. So the images that were used to make this video were taken 9 hours and 56 minutes apart from one another. So we're seeing Jupiter at the same face every time. So it looks like it's just kind of sitting there, but we can see the motion of the different cloud layers. You can see some of them are going from west to east, like the central band here. You can see some are going east to west. You see the Great Red Storm, how it's circulating there. You can even see in individual frames, some of those moons pass in front of Jupiter. And in some of the frames, you can see these dark spots on Jupiter. They appear like right over, like there was one right there. There was one over here just a moment ago, two over here. Those were shadows of those moons. So kind of a neat view to see as we come into Jupiter. So we arrive at Jupiter over the 3 months as we are coming in towards Jupiter, starting in around January of 79. And then we pass by at a closest approach on March 5th. And we continue taking images through early April. Voyager 1 amassed about 19,000 images of the Jupiter system. So what are some of the discoveries that we got out of those images? Well, first of all, we found that there were rings around Jupiter. We'd known about the rings of Saturn. We can see those even with a very, very small backyard telescope, but we didn't know about the rings of Jupiter. Believe it or not, this was not the second planet to be discovered to have rings. It was actually the third. The rings of Neptune had actually been detected before the rings of Jupiter had been observed. And the reason for that is that these rings are incredibly thin. In fact, Voyager didn't see them until it went behind the planet, and Jupiter was kind of blocking out the light of the sun, and we see those rings backlit. Now, what you'll notice in this image, it looks like there are multiple rings here, but that's actually multiple exposures. And so the rings in each of the images aren't in the exact same spot. So they look like there's multiple rings there, but it's actually just one. And so what you'll see also are these very jagged lines. Those are actually background stars. So during the exposure, the probe is moving, and it's also oscillating just a little bit. And that is causing the star trails to kind of have this jagged effect. Okay, so those are just background stars, just kind of ignore those. And the little spots that you might be able to see that look like a grid, that's actually an artifact of the camera. So ignore those as well. So it was determined that these rings are likely caused by meteors hitting some of the very small moons that orbit within the orbit of Io. So not meteorites hitting the large moons, but meteorites hitting smaller moons like Amalthea. So Amalthea was the fifth moon of Jupiter to be discovered. It was actually discovered by Edward Emerson Barnard in 1892. He was born right here in Nashville. He would even use the telescope at the original Vanderbilt University Observatory. So he's kind of near and dear to all of us here at the university and in Nashville. But the rings that we discover around Jupiter actually coincide with the orbit of this moon and several others, some of which would be discovered when Voyager 2 imaged the ring systems. Another big discovery was with Io itself. Remember, that's the closest in of those four large moons. Io turns out to be the most volcanically active body in the solar system. And the reason for that is because it's close in to a very massive planet. Jupiter is very massive. If you took all the other planets and combined them into one planet and even added in all their moons, you still wouldn't get an object half as massive as what Jupiter is. So it's the big planet of our solar system. Now, because of that very large mass, Io undergoes or feels a lot of tidal effects from Jupiter, Tidal. So think about tides here on the Earth. We see water coming in and then going back out in this very regular rhythm. And that's because of the gravitational forces of the moon and the sun. Mostly in this case for us, it's the moon. But tidal forces are not the strength of gravity, it's how the strength of gravity varies from one place to another. So what I mean is, let's imagine that this left side of Io is closest to Jupiter. The closer you are to the planet, the stronger the gravitational pull is. Okay, that means that this side feels a little bit stronger pull than this side over here. So the moon is effectively being pulled. And as it's going around the planet, which by the way, it only takes it less than 2 days to go around Jupiter. Compare that to our 27-day orbit for our moon. So this moon is going around and it's being squeezed and stretched and squished as it's doing that. That creates a lot of internal friction that heats the interior of that moon and keeps it from cooling down. And that's what's driving the volcanism on here. Voyager 1 imaged a volcanic plume coming up over the limb of Io here. So a lot of the features that you see here are not craters. They're actually individual volcanic eruption spots. So like this one right here, a couple of these over here. At any one time, there's about 10 volcanoes going off on this moon. So those are just two of the discoveries from Voyager 1 around Jupiter. So we have the slingshot effect, and we increase our velocity and get sent on to Saturn. So a little over a year later, we have Voyager 1 approaching Saturn. So this is an animation from images of Saturn. And again, here's another one of those very interesting images that is ingrained in my mind from childhood. Another nice family portrait here, this time of the Saturn system. Now, a lot of these moons look very large, but in fact, all of these moons, except for this one, are smaller than our moon. In fact, several of these are much, much smaller than our moon. But this moon up here, this is Titan. So this is one of the primary targets for Voyager 1. So what did we encounter at Voyager 1? Well, with the Pioneer missions, we got some closer views of Saturn and its moons. We saw the rings, but we didn't see as much detail as we would have liked. But Voyager 1 clearly showed how the rings are individually organized into bands. So one of Kepler's laws of planetary motion says that if you're orbiting an object, the farther you are from that object, the slower you're going to be moving. And that's the way the planets are. Mercury is fastest going around the sun because it's closest. Neptune is slowest because it's farthest away. So as the material in these rings gets farther and farther from the planet, the material moves slower and slower. So it would make sense that we would have individual ring bands within the ring system, because all the material in each of these bands is moving at different rates as opposed to its neighboring ring of material. We discovered other rings, especially when we go in behind Saturn and can see the rings from behind and see them backlit by the sun. And we also found shepherd moons that help organize a ring out here called the F ring. So here is a Voyager 1 image of the F ring, and you'll notice it's not nice and smooth. It's kind of knotted in places, and it was often wondered, what can cause that, and it's in fact due to the presence of very small moons that orbit around this ring. On the right, this is an image from the Cassini mission, which arrived at Saturn in 2004 and was there until 2017. But here you can see the two shepherd moons of the F ring. So this is called Pandora. This one is Prometheus. Got an animation from Cassini as well, so you can see how these moons, as they pass by this ring, their gravity influences the particles within the ring system. So you can see there goes Prometheus, and you can see it's creating kind of a wake pattern from its gravitational influence. And so the gravity of these moons helps to confine that ring and keep it from spreading out and getting thinner and thinner and thinner. Another interesting find from Saturn is the moon Mimas. So we had seen Mimas from Earth, but we hadn't seen it up close. If you're a Star Wars fan, then obviously you immediately think, the Death Star here. So it's, which by the way, Star Wars came out a few years before this image was revealed. So, one didn't cause the other. But this moon is pretty small. It's much smaller than our own moon. By the way, ignore these two white dots and this black speck here. Those are artifacts from the camera. What is notable about this moon is that it has a very large impact crater. It's been named Herschel. It's theorized that if the impactor that created this was just a little bit larger, it would have shattered that moon if the impact had occurred. So thankfully for this moon, the impactor wasn't larger, and it bears this really neat looking scar. All right, so the last goal of Voyager 1 was to do a flyby of Titan. So it was able to do that flyby, and it found that its atmosphere was actually much thicker than previously thought. Found that the atmosphere was also mostly nitrogen, and it was even able to, as it was passing by and kind of looking through the atmosphere from the side, around the limb of the moon, it was able to see individual haze layers, which is kind of akin to smog that we would see in large cities during the summertime. But some evidence had suggested that there might be hydrocarbon or organic compounds that could condense and form lakes on the surface of this moon. The hazy atmosphere, however, did not permit direct imaging of the surface. The atmosphere is just too hazy to be able to penetrate it with visible light, but the Cassini mission later on would image it in infrared light and also use radar to map out the surface. And it was confirmed that it does in fact have lakes of methane on it, because the temperature on this moon is several hundred degrees below 0 Fahrenheit. So methane can actually condense into a liquid. But it's thought that the condition, like the chemical composition, might be very similar to what a young Earth might have looked like billions of years ago. So it's still a primary interest to a lot of astronomers. So with the flyby of Titan, that put it on a trajectory to where Voyager 1 would now head out of the solar system, and the trajectory would actually also take it up above the plane of the solar system. So with that, the Voyager 1 mission had basically, or the primary goals had ended of doing these flybys of these planets and that moon Titan. So now Voyager 2, remember, it's on the tail, or hot on the tail of Voyager 1. It would do a flyby of Jupiter, do some follow-up observations, take additional data. The more data you can get, the better. It would then do using the slingshot, it would go to a flyby of Saturn. But here's the caveat. So if possible, then we would have a flyby of Saturn put Voyager 2 on a trajectory for Uranus, and then with Uranus, we would go on to Neptune. But if Voyager 1 had not succeeded in completing its flyby of Titan, let's say there was a malfunction in a thruster, maybe there's an electrical failure, or something prevented the flyby of Titan, Voyager 2's course would be altered so that when it did the flyby of Saturn, it instead would do the flyby of Titan, so that we could get our flyby in. However, that would mean that if we did the flyby of Titan, we would not be able to get onto a course to go to Uranus or Neptune. But thankfully, Voyager 1 was successful in its flybys. And so when Voyager 2 did its flyby of Saturn, it was then put on a course to Uranus and then on to Neptune. So here is kind of a diagram showing how the planets are orbiting, and the trajectory of Voyager 2 shown in that purple there. So you can see that we start out the animation with the planets all coming in kind of right through here. And so we launch at the right time so that Voyager 2 intercepts Jupiter. Jupiter can then fling us over to Saturn. Saturn can then fling us over to Uranus, and then Uranus will set us on a course for Neptune. So as with the previous mission, it was going to do studies of the planets, the moons, and then for Uranus and Neptune, get us our first, and so far only, close-up views of those planets. So just spend a moment on each of these. So we arrive at Jupiter about 4 months after Voyager 1. So Voyager 2 did a lot of follow-up observations. So we had discovered the rings around Jupiter. So Voyager 2 also was going to image those rings. And in doing so, it discovered a couple of more moons that were orbiting in close to Jupiter that were also within that ring band. and help. Looks like that they also helped to contribute to the formation of those rings through meteorite impacts. We would also re-image Io. So here is a quarter of the disk of Io. You can see that Voyager 2 was able to get another volcanic plume in action. In fact, it had observed about 10 volcanoes going off during the flyby. And comparing the images from Voyager 1 of Io to the ones that were acquired by Voyager 2 4 months later, astronomers are actually able to see changes in the surface of the moon in just that 4-month span. So when we say that Io is extremely active, it is extremely active because over 4 months we can actually see a change there. The right side view here, this is a crescent view of the second moon, which is Europa. It has a very icy surface, and what was found was that its surface is covered in what originally were thought to be very deep fractures, but now it looks like those fractures are very, very, very thin, which would indicate that there is a subsurface ocean below that icy surface. So it's not like this moon is, just a solid ball of ice. Looks to have a rocky core, an ocean, and then, and when we say an ocean, we don't mean just, like for the Earth, maybe an average of 2 miles deep. We're talking tens of miles deep. If I remember correctly, it approaches 100 miles or 100 kilometers average density or average depth. This moon is smaller than our moon, and it's not solid water. It does have that rocky core, which takes up a lot of it if it's interior. But believe it or not, it actually has more water on it than what the Earth has. We're not just talking fresh water. We're actually talking about all of the oceans, all of the lakes, all the streams on Earth. You add all that water together, Europa actually has more water than the Earth does. So it's a pretty interesting place. It's not the only moon in the solar system to have indications of a subsurface ocean, by the way. So we do our flyby of Jupiter. We move on to Saturn and encounter it in the mid-1981. And we get some more images of some of the moons we weren't able to image before. So for example, we have Calypso, Hyperion, and Iapetus. And then over here, we see another view of the ring plane, kind of up above the ring plane here. What is interesting in these images, you'll notice that there are some black streaks on the rings. So the rings are all kind of concentric here, kind of going around the planet, but these streaks don't follow that same ring pattern. In fact, in watching subsequent images, we can see that these dark areas, what are called spokes, are actually moving independently of the rings. It's not like they're embedded in the rings. It's like they're above them, moving at a completely different velocity. When astronomers really studied this, they found that these spokes were actually orbiting around the planet at the same rate that the planet rotates. So it's thought that this may be dust that is electrically charged, that is interacting with Saturn's magnetic field. And so as the magnetic field rotates with the planet, this dust moves along with it there. So the Cassini mission, decades later, actually saw these spokes as well. And so they don't stay forever, they do change, but it is thought that they might be composed of dust. All right, so then about 5 years later, thanks to the assistance of Saturn, we now move on to planet Uranus. And so this would be our first, and again, so far only up-close view of this planet. Uranus at first was a little bit of a disappointment because its atmosphere was just so bland. You look at the views of, for example, Jupiter here, and you can see that Jupiter's got a lot of detail in its clouds. Those are constantly changing. Even Saturn has banding in it, and occasionally we'll have pop-up storms that show up as like white ovals and that kind of get elongated over time. But Uranus, it was just kind of bland at first. But it did hold some surprises. So based on how fast its magnetic field rotates around, we now know that it rotates about once every 17 hours. So its magnetic field is also very offset. So you think about the Earth's magnetic field, you can think about like Earth having a big bar magnet inside of it, which is not the case, but you could, just for simplicity's sake, you can view a bar magnet inside of the Earth. And so one end points up towards the North Pole of the Earth, and we have the magnetic field coming out of our Earth. It goes around, loops around, and comes into the South Pole. So that bar magnet for the Earth wouldn't be aligned exactly with our rotational axis, but it's not too terribly far off, okay? But again, that's not the actual mechanism inside of our Earth. Imagine the same thing for Uranus. But for Uranus, if Uranus is on its side and its rotation axis is like horizontal, imagine taking that bar magnet and turning it about halfway up so that it's like that versus the rotation axis, which is like that. So Uranus's magnetic field is tilted quite a bit with its rotation axis. And not only that, but it's offset from the center of the planet as well. So we're not exactly sure why that is, but there are some theories that even though Uranus and Neptune likely have a rocky core and lots of ices on the outside of that, there may be a thin layer of electrically charged material that is moving through that kind of icy material that is generating this electric field this magnetic field, and it may not be uniform. And so the jury's still out on trying to figure out exactly how Uranus has this type of magnetic field. But like the other giant planets, it does have high wind speeds, about 600 miles per hour in some cases. It's not super high. Saturn is actually has higher wind speeds, and as we'll see, Neptune has even higher wind speeds. But we made some more discoveries at Uranus as well. Excuse me one second. We imaged some of the known moons for the first time, discovered 11 more moons. And Uranus, we didn't know it had rings when we'd launched the Voyager missions. But between the time of launch and Voyager 2 getting to Uranus in 1986, observations from Earth had actually detected a ring system just serendipitously. So as astronomers were using what was known as the Kuiper Airborne Observatory, they were observing Uranus, and they were waiting for Uranus, as it's moving along in its orbit, to pass in front of, or the term is occult, a background star. And so doing this, it allows astronomers to learn about the atmosphere of a planet. So if the star winks out very rapidly, then that means that the atmosphere is very dense. But if it just kind of fades out, then you can see that the density increases as you go deeper into the planet. You can look at how starlight is affected by its passage through the atmosphere to learn about composition. So there's a lot of things that you can actually learn through this stellar occultation method. So astronomers were waiting for Uranus to pass in front of the star. And what they were going to do, or part of the data, was that they were going to measure the intensity of the starlight versus time. So we're measuring the brightness versus time. So if you make a graph, as we're waiting for Uranus to move in front of the star, over time the star is still bright. And then as Uranus starts to pass in front, we would see the starlight dim down and then go out completely for a while. And then as Uranus moves out from in front, we'll see the starlight come back up to its normal level and then stay at that level. So as astronomers were waiting for this to happen, they noted that the star's light over time dipped a little bit, just briefly, dipped again briefly, dipped again. And all this happened before Uranus had even gotten to the star. In fact, it happened 9 times. Then finally, Uranus moved in front of the star. And as it came back out, it came up to its original brightness, but then it did that dip 9 more times. And they realized that this is actually due to the presence of 9 rings around Uranus that were not previously discovered. So these rings tend to be much darker. Actually, Jupiter's rings are much darker because Jupiter's rings are actually very dusty. Saturn's rings are very reflective because they're mostly ice. But Uranus's rings are very dark as well. They've got a lot of organic compounds in them. And as light from the sun, especially ultraviolet light, interacts with those organic compounds, it breaks apart those compounds and releases a lot of the carbon. Carbon is a very dark material. Think about a charcoal briquette. That's got a lot of carbon in it. So these rings are very hard to see, but we can see them from the ground now if we observe them in infrared. In fact, the Hubble Space Telescope has also observed them. One other thing about the moons, if you look at the naming scheme for the moons of the solar system, they're named after Greek or Roman deities. The moons of Uranus are not. So for example, this is Oberon, this is Umbriel, this is Titania, and this one is Miranda. So those names may sound familiar to you if you're familiar with the works of Shakespeare or Alexander Pope. So that's kind of a caveat to how these moons are named. But anyway, we learned quite a bit about the Uranian system by that flyby. So our final destination was Neptune, and then encountered it 3 years later. In fact, this past January was the 35th anniversary of the flyby of Uranus. So hard to believe it's already been that long. Astronomers were hoping that Neptune would be a little bit, how do we say, less bland than Uranus, and they were pretty satisfied with what they saw. So Neptune did have more features in its cloud tops. Not quite like what you would see in Jupiter, but it did have some features. So here's a little bit more color enhanced view. So the kind of the hallmark of Neptune is this great dark spot, which was thought to be a storm, kind of analogous to the great red spot on Jupiter. Later analysis suggested that actually this wasn't a storm, but this was more or less kind of a hole in the upper atmosphere that was allowing us to look deeper down into the planet. But nevertheless, this is called the the Great Dark Spot. And a few years after this flyby, when the Hubble Space Telescope first started observing Neptune, it noted that the Great Dark Spot had disappeared. So these spots don't last as long as the Great Red Spot. But since then, Hubble has spotted other great dark spots come about. This one down here was called the Wizard's Eye, for kind of obvious reasons there. And then there was one cloud, because it moved faster due to the zonal winds where it was, that it was called Scooter. So astronomers have a good sense of humor. But the wind speed on Neptune is the highest of all the planets. It's about 1,300 miles per hour. So it's still not extremely well understood how the wind speeds can get this high in some cases. One thing we do note about planets like Jupiter, Saturn, and Neptune is that they radiate more energy, a significant amount more, than what they get from the sun. So that is likely due to, especially for Jupiter and Saturn, that is likely due to the planets still contracting down from their own gravity. And compressing a gas will create heat, and that heat is the central engine that helps to drive weather on these planets. Same thing might be happening in Neptune, because it does radiate more energy than it does get from the sun. So just like on the Earth, storms on the Earth, especially like hurricanes, remember, they form over heat sources like the oceans. So you cut off that heat source when they go over land, and then the storms dissipate. So that may be kind of the driving mechanism that we have to create these very strong winds on this planet. Again, like Uranus, it has a very offset magnetic field, about the same as Uranus, except that it's even offset a little bit farther towards the South Pole than what we saw in Uranus. But once we did the flyby of Neptune, we imaged the 2 known moons at the time, discovered 6 other moons, and also discovered 4 additional rings. Neptune had also been suspected to have what were known as ring arcs, because using the stellar occultation method, if you had nice uniform rings, as Neptune moved in front of a star, you'd see a dip from a ring, and then as it moved out from in front of the star, you'd see the dip from the other side of the ring. When this happened with Neptune, sometimes we saw a nice dip from one side of the ring passing in front of that star, but when its other side started to pass in, we didn't see that nice dip. We saw just a little dip, which would indicate that the rings weren't the same on both sides. So it looks like these ring arcs, you can see like right through here that that's one of those arcs where it's just more material in one place. Looks like that those are transient events because more recent observations have shown that some of those ring arcs are in the process of dissipating. There's some hypotheses about what there might be causing those, but I don't think that the jury has really come back with a definitive idea. And then this is one of the views of Triton, which is Neptune's largest moon. So after we did our flyby of Neptune and Triton, our trajectory now took us below the solar system. So now we're going below the plane of the solar system and kind of seeing it from below. And so this is one of the parting shots of Neptune and Triton. So the planetary visits had been completed and that part of the mission was over. But as Voyagers 1 and 2 are continuing out into the solar system, some of their instruments are still useful and are still returning useful data. So we'll get to that in just a moment. But before we do that, I wanted to highlight this person here, Dr. Carl Sagan. You've probably heard of Dr. Sagan. He was an astronomer and a cosmologist, astrobiologist, writer, and a superb science communicator. So he was on the team that worked with Pioneer 10 and 11, and he was also on the committee. He was the chair of the committee that worked on the golden records for the Voyager 1 and 2 missions. And we'll get to that in just a moment. But what I wanted to really mention him for was in 1990, he convinced folks at NASA to contact the Voyager 1 probe and actually tell it to turn its camera back around and look back towards the solar system and try to get a family portrait of all of our planets. And so it wasn't met with great enthusiasm at first, but Dr. Sagan was a great advocate and he was able to convince folks, and this is the result. So it doesn't look like much at first. You really have to download the high resolution version. But what you see are multiple images overlaid. I forget exactly how many there are, but most of the planets of our solar system are pictured in this kind of mosaic. So you can see the initials of the planets of where they are. So Neptune's way over here, Uranus is here, Saturn's here, Jupiter's right over here. You can see it's kind of bright right here because the sun's like right down in here somewhere. We have Earth and Venus in these two frames. Mercury was too close to the sun, so we wouldn't be able to image that. And Mars, even though it's farther from the sun than Earth or Venus, it happened to be on the other side of the sun from Voyager 1. So it appeared too close for us to be able to see it. But you can actually look at each of the individual images and see the planets in those images. So really a superb idea. This last year was the 30th anniversary of the Voyager 1 family portrait. So really kind of shows our entire solar system. But let's where's our Earth? There it is right there. Let's look at this view just a little bit closer. So here is that little dot right at the tip of my pointer. That is the Earth. Now it's in this streak. That is actually just scattered light from the sun. Okay, so you know, if you look at towards a bright source, sometimes it looks like it's got rays coming off of it. Same thing happening here. But that is our home planet from a distance of about 40 astronomical units, about 40 times the Earth's sun distance. Okay, so you know, about 4 billion miles. But Carl Sagan had a great quote with that, with what he called the pale blue dot. So he said, "Look again at that dot. That's here, and that's home. That's us, and on it, everyone you love, everyone you know, Everyone you ever heard of, every human being who ever was, has lived out their lives. So it's really something to think that that little dot, contains, what is it, about 7 billion people right now, and just how small we are in that vast cosmos. So I'm so glad that he thought of this idea for getting our solar system's family portrait. So we're going to finish up, just talk a moment about where the Voyager missions are now. So currently they are about, so Voyager 1 is about 152 astronomical units from the sun. Remember that an astronomical unit is an Earth-Sun distance. For comparison, at its farthest, Pluto is close to 50 astronomical units from the sun. So Voyager 1 is about 3 times the Sun-Pluto distance. Voyager 2, remember, it's not going quite as fast. It's not quite as far out, but it's at about 127 AU. Now, in this diagram, you see quite a bit of stuff in here. You see a light blue area, you see a dark blue area. And then you see within that dark blue area, our solar system. So I don't want you to worry too much about this dark blue area right now. All I want you to worry about is this light blue area. This is called the heliosphere. You think of this as the environment of the sun. This is where the sun's magnetic influence basically reaches to. So the sun's gravity is still affecting Voyager 1 and 2, but an incredibly small amount. So they're never going to stop and return. They're going to keep going forever. But the particles streaming off the sun basically are limited to within the heliosphere. So this is basically defined by the sun's magnetic field. And so one way astronomers kind of define our solar system is, where does the sun's influence stop? When we talk about particles coming from the sun, that stops with the heliosphere. So if these probes cross the heliosphere, then we should see the cosmic rays from the sun decrease quite a bit, because they can't really get past the sun's magnetic influence. But we should see now a large increase in cosmic rays coming from deep space. Okay, so how can we actually determine that? Well, the probes are still communicating. Excuse me 1 second, get my water here. So the probes communicate with Earth via NASA's Deep Space Network, which is located in 3 locations on our planet. So this one here is this is the Goldstone Deep Space Communications Complex in California. Here's one that is near Madrid, Spain, and then here is the one that is near Canberra, Australia. So these are strategically placed so that when we send a probe out to, say, Jupiter, as the Earth is rotating, if we just had one station, then half of the day our station would not be able to see that probe because we'd be on the wrong side of the Earth. So these have been located 120 degrees around the globe, so that as one station starts to rotate out of the field of view of the probe, the next one is rotating in. So at any one time, at least one of these is going to be able to see a probe that is, say, on its way to Jupiter. So these are the ones that are able to detect the extremely faint signals emanated from these probes at a distance of 120 to 150 astronomical units. So these dishes here, these largest dishes, are about 70 meters, or a little over 200 feet wide. The one in Australia, remember I said before that Voyager 2's trajectory after Neptune took it down below the solar system's plane. Australia is the only one of these stations in the southern hemisphere. So this station is the only one that is able to communicate with Voyager 2, whereas these two can communicate with Voyager 1. This dish just recently finished some upgrades. It took about 8 months. So for 8 months, we hadn't been able to communicate with Voyager 2. But the upgrades were specific. Some of them were specifically for communicating for Voyager 2. We were able to reestablish contact, and we still have a signal from Voyager 2, and these guys are still seeing a signal from Voyager 1. So how do we know they're outside the heliosphere? So here are some plots from Voyager 1. This is from the cosmic ray detectors. On the left side, we've got the number of particles detected per second. Okay, so this is about 31, this is about 30, 29, 28, and so on and so forth. And then all of a sudden, you see this very steep drop down to about 2, 1, and then basically we're at 0 now. Okay, so if you look at the date, see October of 2011 here, December 2011, now we're into 2012. We started getting a count of 0 low energy cosmic rays, or in other words, cosmic rays from the sun, around August 25th of 2012. That same time, we see a large jump in high energy cosmic rays, those coming from outside of our solar system, like from supernovae. So both of these graphs suggest that Voyager 1 crossed the heliosphere in August of 2012 when it was about 120 astronomical units from the sun. We saw similar graphs in 2018 when Voyager 2 crossed the heliosphere, also at 120 astronomical units. So they are still broadcasting. They're not taking images. Some of the instruments have been turned off to conserve power, because remember, the radioactive decay is decreasing over time, so power is decreasing over time. So only the bare bones instruments are being kept on, and ones that need to be kept on, such as the cosmic ray detectors. Let's see. I'll show you one website in just a moment that we'll end with, that will give you some more details about what they're up to at this moment. I just wanted to touch on what the golden records were. So here's one of the actual golden records. Here's its cover over here. And these were the ones that were mounted to the side of Voyagers 1 and 2. So here you can see John Cassani, who is the Voyager project manager in 1977, holding the US flag. And this is the record and the cover for Voyager 2, seen in the background there. So what's on those records? There's a message from the Secretary General of the UN. Greetings in 55 languages, sounds that you find on the Earth, like that of a whale, thunder, heartbeat, laughter. There's even some artificial sounds, like I think a car engine is on there. About 90 minutes of music from Eastern and Western cultures. And then, so that all of that is on one side. Then on the other side, encoded in analog, are 115 images. Okay, so I won't go through how we actually do that encoding and decoding. That's an entire talk in and of itself. But on the other side of the record, if you decode the signal, you'll be able to get 115 different images. On the cover itself are instructions for whoever comes across this probe, how they can actually get the data off of there. So we see a diagram showing the record and the stylus or the cartridge and the needle that are packed away with it, showing how to orient the record, where to put the needle. And then here's basically a diagram of the signal and how you take that signal and convert it into an image like this. We also have a reference showing where our solar system is in reference to 14 pulsars, which are a special type of star that kind of stick out like a sore thumb, so to speak. And then, so that will give folks an idea of where we came from, but then they may ask, well, how long ago was this actually sent? And electroplated onto the cover is a little bit of uranium, I think it's 235, that has a very long half-life of several billion years. So by looking at how much of the uranium is left, how much it has decayed into its other products, we can actually one can actually figure out how long ago this craft had been launched. So so with that, I'm just going to go over to this one website here and just kind of give you an idea of what it looks like. Let me do one more share screen and then we'll do some questions. And it is really starting to storm, so I hope my power doesn't go out. So anyway, this is, I think this is called Eyes on the Solar System, but you can just Google search JP or Voyager mission status. and you'll come to this page. It'll give you all the details about how far the probes are, how long it takes a signal to get to them, and then also be returned back to us. Gives you the current cosmic ray counts. So we're getting data back on essentially a daily basis from these probes. Here are the list of the different instruments that are on board and which ones, you see which ones have been turned off. So like our cosmic ray subsystems are still on because they're the ones returning the data we just looked at. But over time, as the RTGs decay even more, some of these other systems will be shut off until we finally just don't have enough power to be able to send a signal, which is projected to, the final signals will be sent and received sometime in 2025. So finally, down at the bottom is a really nice visualization. I would recommend putting this full screen. You can drag it in 3D, and you can see where the missions are with respect to our solar system. You can go to other objects like, for instance, the New Horizons probe and see where it is. You can learn about it. You can drag it around and see where it is in our solar system. You can even compare it to other things, like here's New Horizons versus the Juno spacecraft around Jupiter, OSIRIS-REx, Parker Solar. Let me find another one here. Yeah, there we go. Compared to Voyager 1, things like that. So it's a really cool site, so I definitely recommend that you check it out if you get a chance. So with that, I am not too terribly far over an hour, but that was a lot of fun info, at least in my opinion. So with that, I'm going to stop my share and see if we can't take a few questions here. So let me bring up my chat. So it looks like there aren't any questions at the moment. So, you know, people may be formulating questions or thinking about what we've talked about, but I'll, you know, give everybody a few more minutes to ask any questions if there are, and if there aren't, then that's fine. Who knows? We may have people sheltering from the storm right now because it's coming down like crazy out there. So I still don't see any questions. It's fine. So again, I just want to remind everybody that we have a couple of events coming up in April. Again, all virtual events. Definitely check out, let me go to our webpage here. Definitely check out our, hold on one second, let me find it here. Wow, it is hailing. It sounds like baseball's hitting the roof right now. All right, so just check out dyer.vanderbilt.edu, our homepage, and you know, we'll have links to all of our different events there. One question was, what will happen when we lose signal? Well, unfortunately, when we lose signal, there's not really going to be anything that we can do. We can just look back at all the images. Astronomers are still looking at the data that's being sent back and has been sent back over the decades and finding more information to pull out of it. So yeah, I'm hoping that they'll last for another, you know, couple of years. It'd be great to hit at least 45 years in space, but you know, I just thank the missions for all their service and all their you know, beautiful images and data that they've sent back, and which again, you know, has really had an effect on me and really kind of altered my my course in life. So, all right, well, with that, everybody, I think that we will call it an evening. Again, I want to thank everybody for joining me, and thank Brian Smokler and Helen Morset for their help as well. And I hope to see you all here in April. So everybody have a great night.